day. We have Taylor here today, who is a professor in material science at the University of Utah, who will kind of tell us about GANS, a super cool generative model, a bit an alternative to those models we have discussed on Monday. It's like an implicit model. And then you will talk also about some cool application in material science and show how this model, how GANS can be used for material science. So super excited for the talk.
Okay. It's a pleasure to be here. I'm sorry I couldn't be here all week. I saw the speakers and I was jealous that you got to hear from these amazing people, but I had a daughter's birthday party right in the middle and I didn't want to miss it. So thanks for bearing with me and for rescheduling to the end of the week. I appreciate that. In some way, maybe it's fitting that we're talking about GANs at the end because in the deep learning space, they've become a bit of an afterthought. And I'm going to try and argue today that maybe they shouldn't be. Maybe they're still worth looking at. In fact, I tried out on all the major language models and asked, are GANs over in science or should we still be considering GANs? And the resounding answer is yes. And I'm going to show you some reasons why. So first off, I'm from the University of Utah. If you haven't been to Salt Lake City, it's gorgeous. It's a bit like Berkeley, tucked up against the mountains. What I like the most about it is that I can be from my lab here up skiing in about 30 minutes. This is actually our material science student group, our materials advantage student group, did a backcountry ski outing. And then I found out that the university didn't like that for liability reasons. So it's no longer an official university backcountry ski outing. We just go skiing. So you've heard all week about some amazing generative models. I've seen some of the topics that you've been hearing about. And GANs are just one of many, right? They're one of many generative models out there that you could choose from. And in some ways, they're a kind of a pain in the butt. Like they're not as easy and straightforward to implement or to train as some of the other ones. I'll show you reasons why in a moment. But their outputs are pretty good. You've probably seen a variation of this slide before. This came from Ian Goodfellow, and I'm sure you know that this is the inventor. What maybe you don't know is that he did it while he was a grad student, which I think is awesome. It was back in 2014. He was at the University of Montreal. Ian Goodfellow puts that image up on the far left there, that 2014. This presumably came from his thesis work. It was the very first time that in came random noise to a neural network. Out came something that looked a bit like a face, right? So fast forward only 4 years and he does the tweet, right? So it ended right here when he posted this on whatever it was, right? And the point of his tweet then was to say, in 4 years, look at this crazy progress, right? Now, since then, we've come a long way since 2018. I added this one from 2021. This was NVIDIA's advancement, which allowed them to add fine details. And even as the face moved, like the beard hairs would move with it, pretty impressive. And nowadays, it's even crazier, right? Again, it's 2023, it's not even nowadays.
How were you able to maintain, like just not get sick during the flight scenes?
It's really peak fitness, Howie. You know, I'm always multitasking. So I got sick. I mean, a lot of those G's, I vomited, but I kept my mouth closed, I swallowed it. So the camera never notices, and it's pretty good protein.
Do you enjoy fame?
I enjoy pushing myself to the limit. I enjoy the breath control, doing interviews on podcasts while also maintaining peak fitness regimen. What's your problem with UV rays, Howard? How come you're always wearing glasses?
All right, so that comes from something called Deep Face Lab. It's one of the many different, deep fake technologies out there. Let's take a look at that one real quick. Deep Face Lab. I was curious about that because I wanted to know what was sort of the state of art here. So let's do Deep Face Lab. Let's find their GitHub repo. Make this a little bigger so we can see it. They actually archived it 6 months ago or so, right? It's been around for quite a while. If I'm guessing everyone in here is familiar with GitHub, but you can sort of explore what they're doing in their models folder. If we select their models folder, the model they're using is this one, this SAE, high definition. And when you actually click the model, I promise I'm going somewhere with this. If you were to start exploring this, and we won't go in much detail today, but as you explore through this, make this a little bigger. Here where they actually initialize their model, it's a big old model. Like there's a lot of stuff here and a lot of options, but if you explore for not very long, You're going to find out what type of architecture they're using right here. They are actually using a GAN. So what you just saw was a GAN, and later on they define their generator, they define their discriminator. These things are very good. Arguably, I think the output of GANs are better than even diffusion models, but with the flip side that they're a pain in the butt to train, right? They are prone to instability, and I'll explain what that means in a moment. But I guess what I'm trying to get with this message across here with this slide is that these are still state of the art. They are still very, very good. All right. So what exactly is a GAN? I'm guessing everyone in this room, if you're at a deep learning conference, has already seen some variation of this, but a GAN is its name, generative adversarial network, implies that you have two different networks competing against one another. And that's critical because if we just had one network, it wouldn't be able to do what we want it to do. Let's imagine a scenario where we just got one network. If you look in this slide, we're just going to have a discriminator neural network, okay? Now, the inputs to this are going to be, we're going to have the discriminator, like its name suggests, it's going to try and discriminate real from fake. So we're going to be able to send it lists of images or crystal structures or weather patterns, right? This is domain agnostic. Real examples of inputs and fake examples of inputs. And the task that we're giving the discriminator is to classify it as either real or fake. Typically, that's done by assigning it a value of 0 or 1. And then obviously we calculate a loss based off of typically something like a binary cross entropy. And we use that to then, via backpropagation, update the weights of our neural network to make it even better the next time around, okay? This is fine, and this does a good job as a classifier. We call it a discriminator, but this is really a classifier, right? But a classifier can't generate something new. And these class of generative models, that's exactly what we want them to do. Instead, basically, it's just able to find the underlying trend of what makes something real versus fake, as opposed to use that distribution to make something new. Here's a good example, which I stole from YouTube, right? Shown here is an example of some sort of distribution. Now, you as humans, we can really easily look at patterns in low-dimensional space, and we can find the patterns, right? There is an underlying distribution to here. You guys can see that in these three data sets, the underlying distribution is a sinusoidal curve, right? I guess like a inverse cosine or whatever it is. So there's our underlying distribution. And so if you were to use a model to generate data once it found this underlying distribution, what it's going to do is just this. It's going to drop data points directly on that underlying distribution that it's found. But what we actually want the generative model to do is obey the general trend, but exhibit the same sort of variability and ability to depart from the exact trend that we see in real data. And your discriminator is not able to do that. So Ian Goodfellow back in 2014 is scratching his head thinking, how do we figure out a way to get, yes, the underlying trend, but also some variability? And that's when he introduced the generative adversarial network architecture. And all we had to do was, instead of what you saw before was, previously we had real structures up top and a list of fake ones down here. Now all we're going to do is we're going to add a generator whose job it is to generate the fake compounds. And the benefit from here is that now what the generator can take in as an input can be, sometimes it's called white noise or chemical white space. It's a much broader space over which we could be generating structures. This is where the sort of imaginative structures can be generated. And you can put constraints on this if you want. This latent space, you could carve off regions of it. Imagine if you're a chemist, you know that there should be no such thing as for example, a noble gas oxide, right? So you could try and carve regions off and say you're not allowed to go there. But for the most part, we don't have to do that. Instead, what we do is we say, let the generator take as an input anything, and instead let it transform that anything that we give it, transform it to a distribution that more or less matches real materials. And GANs are pretty good at that. The generator neural network is a pretty good tool at generating distributions that match other distributions. So it does a pretty good job of learning, as it were, that there's no such thing as a noble gas oxide, right? All right. The trick, though, is that now that we've got two different neural networks, we have to train both of these things. You could try and train them simultaneously, but that's not what they do. Instead, they train these things iteratively. We take a pass through our data, through our architecture, we train the discriminator, right? And we calculate its loss, update the neural net, so we've done a training step. And then we do the same thing, but for the generator, and you alternate back and forth between these. It's challenging because in a normal neural network, backpropagation goes all the way back. And so everything has a strict definition based off the gradient on what to do to update it. Here we don't have that. You've got two different networks that are competing with one another and they have different objectives. It's often referred to as a mini-max game because one is trying to minimize the loss function and the other one's trying to maximize the loss function. And because of that, this mathematically becomes actually pretty fraught with, there's a lot of math behind this actually, if you want to get into it. And in terms of practical application, what that translates to is that these are unstable. They tend to be highly unstable. And just by raise of hand, who's tried to train a GAN before? So maybe 20% of people in here. What's been your experience? Does it work beautifully every time? So true story. I had my a student. I've only had 2 students bail out of my group. One's actually here at Berkeley now, and God bless him. He's a good guy. Another one spent a year trying to train GANs. Was like, this sucks. I'm gonna go be an experimentalist, and that's fine too. Yeah, they're hard because you'll spend a week of GPU time that you had to beg and plead for, and then all of a sudden it diverges. If anybody's done Rietveld refinement before, I know this is not strictly material scientists, and the fitting all of a sudden diverges because as it was adjusting in this case, the aspects of the crystal structure, and then all of a sudden it made too big of a change, then it just blows up and you lose all your progress. That same thing can happen in these GANs, which is a total bummer, which is why people don't use them because it's kind of a pain. But I think that we should, and we should just learn ways to make them more stable. I'm going to show you a couple. So really quick, let's go through this mini-max idea and the loss function. Why are we trying to minimize one from one perspective, maximize it from another? So up there is our expression. This is our loss function that we're going to try and calculate, right? It has to be done for both neural networks, D and G. Again, we're going to do them iteratively, first D and then G and then alternate, right? But we've gotten it written out for both. What you're trying to do here in that expression, I'm loath to show mathematical expressions, but since it's a summer school, let's go through it. This E of X from a distribution of X, all that's saying this is the expectation when you send a real value X through, taken from some distribution of real data. If you were to take that X value, which represents a real whatever, and you put it into your discriminator, right? And then we take the log of that just to scale it. That's the expectation there. That's this first term. In other words, this is the discriminator's prediction on real data. We'd like that, if you're the discriminator, you want that to be as high as possible. You want to do that correctly, right? Sorry, the loss you want to be as small as possible. But if it's fake data, which we're going to call Z, this is the imaginary data, right? This is just sampling from our latent space, taken from some distribution of the latent space available to it. We're going to notice the difference here. We're not going to send it straight to the discriminator. First, we send it through the generator. So it's G of Z. We send our noise essentially through the generator. And then the output of that goes into the discriminator. And then we do 1 minus that because you want to get that one correct. If it's fake, then we want that to be 1 minus. So this is kind of interesting. The second one represents the discriminator's prediction on fake data. And really, now you can see why we want to minimize it versus maximize this from the 2 different perspectives. So the discriminator wants to maximize this overall function. The generator wants to minimize it. Okay? Let's walk through the steps of how this happens. Okay? So again, every time that we do a training, it says for K steps, as many steps of your epochs, for example, that you want to do, here's what we're going to do. We're going to sample some amount of noise samples based off of your batch size. We're going to call our batch size M here, right? So make a bunch of these potential samples. We're going to transform them using our generator. We're also going to take that same number of samples, but these are going to be sampled from real data. And these, we're going to use that data, our X's and our Z's, our real and our fake data, and pass them through. With this, we can update the discriminator by doing ascending the gradient. Instead of gradient descent, this is gradient ascent in this case. Right? So we're going to go one by one through those. So X sub I, Z sub I are the individual samples of our real and our fake data. We're going to do that in some batch, M size batch, and we're going to figure out what our loss is for this. Once we calculate our loss through the magic of PyTorch, the fact that they can keep track of the mathematical operators necessary to get a gradient, we can easily come up with how we need to adjust the weights of the neural network, in this case, the discriminator. Okay, so we will use this ascending gradient to update the discriminator only. Then you end that part of the process, and now we're going to turn our attention to the generator. We're going to use, we don't actually have to use the same data as before because we don't need the real samples, right? We only need the noise samples. Why is that? Well, because we're looking at we're looking at derivatives, right? And if you look at this expression, if you took it with respect to the generator or the discriminator shows up in both of these terms, but the generator only shows up in one term. And the generator term over here only uses fake data. So you don't actually need real data for the second step. So you'll notice here that in the second step, we only sample noise, right? We don't have to sample real data because that other term is going to go to 0. But anyways, the point is once you've got these new data points, just like before, for some batch size, you're going to go through and one by one calculate how far off they are and use that. But this time we're going to descend the gradient, okay? So that, at least in principle, is how this works. I'm going to have a Google Colab notebook at the end of today's lecture in about an hour. We're going to hop over to that, and we'll show you mathematically what this looks like. It's not too bad, okay? Here comes the bad part. The bad part is that training is difficult. 2 years of your life, I hear you. The biggest problem is that this is what we call a non-convex game. In mathematical terms, this means that there's not a single global minimum. If you can think of like a lost surface, there's many minima, and there can be even maxima. And so it's really hard for you as a user of this tool to know whether you have trained this to the best that it can be. In fact, you never know. That's one of the whole points here, something called the Nash equilibrium. Nash equilibrium is when you have, think of like somebody playing chess, like you've got two people playing chess with each other. Nash equilibrium says that you can't, I'm going to get my definition wrong, let me pull it up so I don't get this wrong. Nash equilibrium says it's a concept from game theory that applies to the situation where two or more players are involved in a game. Each player has chosen a strategy where no player can benefit by changing their strategy while the other player keeps theirs unchanged. Like when I was a kid, I used to like try and pester my sister, and she would at some point result to the final strategy of sitting on the couch and like kicking, right? And there's nothing I can do at that point until she changes her strategy and tries to run to the other room, at which point I can change my strategy. This is Nash equilibrium. In other words, how does that translate to the GAN? In the GAN's perspective, what that means is that if the generator is doing a great job of fooling the discriminator, it has no motivation to change what it's doing. This is what we call mode collapse. I'm going to show you an example of that later. Okay, or vice versa with the discriminator. If the discriminator is doing a great job of figuring out the real from the fake, then it has no motivation to update its approach either. This is the problem with a non-convex game where we have this Nash equilibrium. In short terms, what it means is that there's not an easy mathematical way where we can just grind along the gradient and get to the best solution. Instead, you have to perturb the system. You have to perturb the system in order for it to find the best solution. And this is just hard to do. So mode collapse, you'll hear that term a couple times today. Mode collapse is when a certain solution keeps on fooling the discriminator, and so it never changes. The generator's figured out a good way to fool the discriminator, so it just sticks with it. Vanishing gradient, you'll hear about that. If the discriminator, on the other hand, is outperforming the generator, so the discriminator can very easily tell real from fake, which is, spoiler alert, usually the case, especially in the world of material science where I'm coming from. It's way harder to generate a realistic material than it is for a discriminator to say real from fake. And humans do the same thing. If I show you a bunch of crazy crystal structures, it's easy for you to say, like, those are nonsense. These are the real ones. So this vanishing gradient problem is common for us. What happens is that the generator's gradient vanishes, and therefore the generator can't learn, which makes the discriminator even better, which is like this feedback loop, which just breaks it. But you can have the other scenario. It's less common. The exploding gradient problem is the other way around. In this case, the generator is doing such a good job of fooling the discriminator that the loss function can escalate for the discriminator, and the gradient will actually get too large, and you get the opposite problem. So really the trick here is a balancing act between your discriminator and your generator. And again, like the name suggests, you're going to adversarially train these things. In practice, what I've found to be effective is that you actually usually have to handicap one versus the other in order for it to train stably. Okay, so what are some things that we can do to do that? Oh, by the way, and yeah, these things are highly, highly sensitive to the hyperparameters, and there's a lot of them: learning rate, batch size, and definitely architectures. I've got 10 slides coming up on architectures. But things that we can do to try and fix this is, first off, we can explore different loss functions. I'll show you vanilla versus Wasserstein in a couple slides. We can do regularization and then explore lots of different architectures themselves to give additional information to the generator or the discriminator. So this brings us to the next part of the talk. Maybe we'll pause for a moment. Are there questions on the basic concept of a GAN so far that I can answer? Yeah. Yeah, good question. Like, can we send in simple metals and complex, zeolites? Yes, but just like if you tried to have it evaluate images and you're sending it a bunch of like 10 by 10 pixel, very small things, and then a giant high definition Rembrandt or something, they have to be the same type of input. We do have to make sure that the inputs are the same. So in terms of crystal structure, that means we have to think hard about how do we make sure that we can represent simple structures and very complex structures with the exact same size input. And I'll show you later in my talk today how we achieve that. But it is possible. You don't have to do it that, by the way. You could stick with just one class versus the other. All right, so if there's other questions, feel free to stop me anytime, but maybe we'll pivot now and talk about, oh yeah, Anubhav?
Just a quick question. So the discriminator always considered the generated samples to be false or fake data
If it always did?
in the loss function.
Okay.
The discriminator would always consider anything from the generator as a fake.
Yeah, if it knew it came from the generator.
Yeah.
Yeah.
But as generated samples become really good, we might want to promote that to being like, okay, this is actually like a real place. This is actually like a real.
Yeah.
Is there any frameworks that do that and say like, okay, let's start promoting some generated samples?
Yeah. At the end of my talk today, I'm going to circle back to that. But what he's basically saying is like the peril here is as the generator gets better and better, you can mathematically actually show this. There's a proof that shows that the generator's loss function will go to 0 if and only if it is producing samples that exactly match the distribution of the trained data. Okay, so it's going to try and do that. But Anubhav, I think correctly is asking, do we want it to do that? Do we want it to just generate the data we already have? Of course not. That's like going back to the discriminator problem where it learns the underlying distribution so perfectly, it will put data points exactly on that distribution without the variety and the variability, which we are expressly trying to use this for as a generative model. So I'm going to come back to that later, to that exact question. Okay, so not even 10 years, about 10 years ago, somebody came up with this concept of the GANS zoo, right? When you go to the zoo, there's all the different animals and they're all organized for you. Somebody created the GANS zoo, right? Here's a GitHub page. They stopped updating it 7 years ago because it was getting out of hand, right? What this author was trying to do is they were looking in the scientific literature, not just material science, all the different deep learning literature. And every time that somebody introduced a new named GAN, and you can see some examples here, it's just the first like 20, right? Adventure, adaptive GAN, AdaGAN, Actual, AtGAN, right? Every time they came up with a new one, he kept track of it and wrote down the paper that it came from. And you could see that this became like not a fun hobby to have very quickly. It was going nuts. And this ended in 2018 or something. Nowadays, there would be probably tens of thousands of unique GAN architectures out there. So why are there so many different, like, why don't we just stick with one or two? Let's sort of explore that. Okay, so I'll begin. This was totally subjective with me with the help of some AI to clump these into clusters. Here's the 7 that I've come up with. Feel free to disagree. But I'm going to start with our core GAN architectures. And this includes things like a vanilla GAN. If you've heard the phrase vanilla GAN, this is basically the very, very simple GAN architecture that our friend Ian Goodfellow came up with 11 years ago up in Montreal, right? The key parts of this is that it definitely has to have a generator discriminator. All these things do. But the only features that these algorithms used were fully connected layers, right? They didn't get too crazy. They were just fully connected layers. And the problems that this obviously ran into is mode collapse and instability during training, which are pretty big problems. And the outputs of vanilla GANs are not very good. I'm going to show you some examples of crystal structures later. They're pretty underwhelming, okay? They do come up with a basic image generation, and they're fine for sort of proof of concept, but they're not very good. So let's move to our next core architecture, and this is now the deep convolutional GAN, DC GANs, right? And the big innovation here is that instead of just fully connected networks for both the generator and the discriminator, we could consider putting those into either or both of those networks, is introducing convolutional layers, right? Those here are, I'm very sure, are familiar with convolutional neural nets, do a great job of learning trends in high dimensional space because they learn the features as they go through the filtering process and the kernel selection process. This is also about the time that we started to see the introduction of batch normalization, other activation functions like ReLUs that hadn't been used originally to introduce some nonlinearity. And the end result of this is that it did stabilize training, and it definitely got some higher quality images. So this would give us your sort of basic image generation. And then the last core type of GAN architecture is our Wasserstein GAN. The Wasserstein GAN uses the so-called Earth mover's distance. Just quick raise of hands, who's familiar with the Earth mover's distance? Maybe I'll go over it then. So the idea behind the Earth mover's, in fact, why it's called the Earth mover's distance. If you imagine two piles of dirt, my kids love to play in the dirt, right? So let's imagine two hypothetical piles of dirt. You could ask yourself how much work it takes, bucket by bucket, to scoop this pile of dirt to make it look like that one, or vice versa, right? Hence why they call it the Earth mover's distance. What this really is, it's actually a distance metric. If you're trying to compare two piles of dirt, one way to compare how different they are is to go chunk by chunk and move it over. One could imagine that if this distribution here in blue had been shifted over a little bit and it overlapped the green a little bit, then that overlap would be dirt we don't have to move, right? You get the idea? So the idea behind these Wasserstein GANs is we're going to use this concept to measure difference. This is a pretty big difference because in the vanilla GAN architecture, what we did was we boiled it down to a single node typically, right? The discriminator takes in as an input some large number of nodes. If you're talking about an image, like a 10 by 10 pixel image, then it's 100 values, right? So 100 nodes. It goes down in either one or many steps, right, to a single node value. And the value on that single node, after it passes through a sigmoid function, that gives you the 0 or the 1 that says real or fake, okay? So you're asking a lot of that discriminator. Take this really high dimensional in the world of crystal structures where I come from, the inputs are huge. They're pretty gnarly. And you're hoping that you can boil all that down to a single 0 or 1 and do that accurately. And through the magic of neural nets, sometimes we can, but not always. The Wasserstein GAN takes a different approach. Instead of using this Kullback-Leibler divergence or Jensen-Shannon divergence, which is what these other ones do, it does something different. Instead of trying to squeeze that value between 0 and 1, where that is the measure of true versus false, it doesn't use a softmax sigmoid at the very end final neuron. It just lets the value be what it is. So you squeeze it down to a single neuron, just like before, but you don't hope that that's the perfect measure. Instead, you create a distribution, right? So the critic, it says here, it outputs a single scalar score, not a probability between 0 and 1. This score represents how real the input is, but it is unbounded. It no longer has to go between 0 and 1, so it could give you high numbers or whatever, right? For a given batch, these scores get accumulated into a distribution. So you could literally run like 100 of these things, and then you could plot a histogram of them. And like maybe your real sample distribution looks like that. And then you do it again, but this time with your fake samples, you generate another distribution. And if you were strictly doing like the actual Wasserstein distance, you would then take that distribution, whether it's normal or not, you would try and plot it as a cumulative distribution function, and you would take the area under the curve via integral to actually mathematically take some extra steps. I didn't know this. I was actually learning this myself when I was going over this morning. I thought that's what it did. It doesn't do that. In the deep learning world, they take a super chintzy shortcut. What do? They just take the mean. That's all they do. They take a bunch of samples that they run through that were real, right? So you got a whole bunch of numbers. I have a visualization later today. We'll see this in action. And they just calculate the average. And then they take a bunch of fake samples and they get a distribution. And they take the average and they just subtract the difference, right? That's what the Wasserstein GAN does. So it's a really cheap and dirty fast way to an approximate of the Earth mover's distance. It is not the Earth mover's distance. It's an approximation. But doing this is much better, because now you're learning on, assuming your batch size is big enough, which is a big if, you're learning how to match the distributions better than trying to get the prediction right on every single sample every time, which is a very hard task to do. So that's our third core architecture with these three. Again, our vanilla, our deep convolutional, and our Wasserstein. There are some other things that got introduced with the Wasserstein GAN. Other key features are weight clipping, gradient penalty, both, and hyperspectralization, but I didn't include that. These are all meant to have this so-called Lipschitz continuity, which improves stability. So what is that? Well, you're familiar with neural networks at the end of a deep learning conference, so I don't need to bemoan this, but you know that as you connect networks from one to the other, it really boils down to this pretty simple thing. The value on your node that's forward in the neural network depends on what the previous values were, multiplied by some weights, plus some bias, right? And then you do this for all of them, you fully connect it, and you send it through some sort of activation function. So normally, during backpropagation, we allow these weights, we don't put restrictions on them. We just say backprop will tell us what the weights can be, and we'll just use them, okay? Instead, we rely on the activation function to condense the values of the nodes down to reasonable numbers, right? The whole point of this sigma function here is to squeeze the output of this, usually between a number and 0 and 1 or thereabouts, right? It doesn't have to be a sigmoid, but it could be something like that. And therefore, we don't have to worry about adjusting the weights because we're hoping that the activation function will do it for us. So in weight clipping, they don't do that. In weight clipping, just like you can clip the wings of a bird, we're going to clip the values that the weights can be. We don't let them go beyond some limit, right? And you can choose which limits to set it to. Commonly, it's minus or plus 1%, right? Could be something else though. And what we're trying to do here is enforce what's called Lipschitz continuity, which is really just saying that the input, whatever goes into the discriminator and what comes out at the end, they can't change very much. Because if it wasn't Lipschitz continuous, it would have large variation of mathematically just like this. It means that the absolute value of the function between 2 points, right? At any 2 points in the inputs, right? If you took the absolute value difference of the function, it must be less than or equal to k, some constant that you decide on, times the variance in the data itself, right? So if you had a function, some sort of crazy curve that changed a lot very rapidly, then it would have to have a large value of k to be Lipschitz continuous. Usually they want a Lipschitz continuous value of 1, meaning that this is just just saying that this needs to be a relatively smooth function. And the way that you can help it be smooth is by clipping these weights. So they'll fix it to be between a certain range. And you can see that mathematically or graphically in this image here. Here's the critic output. You can see that it has been clipped with this orange line. It doesn't allow it to go beyond other ways. Now, that's just one way that you can enforce a more smooth function that's less likely to diverge. There's other ways. You can introduce a gradient penalty. A gradient penalty doesn't mess with the weights. Instead, it introduces a penalty on the loss function. So now it says on the loss function, it says it penalizes the discriminator if the gradient of the output with respect to the input is too large. So this is a more flexible way than just weight clipping, but it's trying to achieve the same thing. So if you see a WG GAN, so that's the Washington GAN GP, the GP stands for the gradient penalty. And then the last way, which is a little bit less common, is hyperspectral normalization. And this refers to normalizing the discriminator's weights or their activations across feature dimensions. The same goal, though, we're trying to stabilize things. Okay, so those, believe it or not, as complicated as those are, that's our easiest class. That's just the core GANs. There's 6 more. So I won't go into crazy detail because I want to save some time for some example, but let's go through a few others. The next big class of GANs out there are what we call conditional GANs. And honestly, this is probably what most of us want. The ability to generate something randomly is great, but we usually want guided generation. You saw this with diffusion, guided diffusion, right? I don't just want to train on a bunch of pictures of dogs and have it generate random dogs. I want a Saint Bernard with a top hat, right? I want specific things. So we can do that with a GAN. We have to condition it though, which means we have to change the information that comes into it. So the first one, this conditional GAN, it conditions the generator and the discriminator on auxiliary information like a class label. So now not only the input could be the input representing a crystal structure, but you could have a label on it, like a band gap or a strength or whatever, right? If it's a picture of an image, it could be the pixels plus a label of what's in that picture, right? That's the additional information that's coming into it that's going to allow us to do conditional generation, right? Adding that label, embedding it, attaching it to our embedding. Similarly is the auxiliary classifier GAN, @GAN, right? This is almost the same, except instead of knowing what the label is this time, this is going to predict the label. This is going to attach a probability of being different classes at the end of it, which is a subtle difference. In one case, you knew the label, using that to guide it. In this case, we're actually predicting the label as well, okay? Then there's image to image GAN. A good example is pix to pix. So this makes an input image to output images using paired data. So for example, you could take a sketch and have that sketch turn into a photo. Google, all the different, AI tools out there are really great. If you go to ChatGPT right now and you say, take a picture of me and turn it into something Studio Ghibli, that's basically a pix-to-pix model. Now, I don't know if they're using a GAN. I don't know what tools they use under the hood, but it's that same idea. whenever you want to match something so it retains the same form, you guys already know this because you've learned about diffusion, but that means you know that there's going to be a U-Net involved for sure, because a U-Net does a really great job of learning details but preserving overall features due to its unique architecture. So this has a U-Net involved in it in the generator. There's cycle consistent GAN, sometimes called cycle GAN. This is another image-to-image tool. It's similar to image-to-image GAN. Okay. The trick here is that it has bidirectional mappings. You don't just learn how to go from me to Studio Ghibli me. We learn how to go from Studio Ghibli me back to me, right? It's a bidirectional encoding is the big difference in cycle GAN. And then there's text to image GANs. That should not say pix to pix. What I think is cool about this is that a student from my group was actually one of the pioneers in this area, which is so cool. This is Ryan Murdoch, who went on to get hired by Adobe. If you've ever used Adobe Firefly, that was him. Get this, he was an undergraduate who reached out to me when I had a summer research project for undergrads, and he was a psychology student. And he said in his application, I like to build neural networks for fun. I was like, you're hired. I don't care if you're a chemist or not. Let's hire you. And he went on to do some amazing stuff. He's had some awesome write-ups and lots of great sources. He was one of the early people here. But the idea here is that, again, this time you're going to have an input, but you're going to attach to it not a label, but an additional bit of information, in this case, a text embedding, right? We know that we can take words. You've had language models, so you already know all about this, that we can take words and turn those into a vector in an embedding process, word to vec, glove, BERT encodings, whatever you want to use, right? And then that becomes the tool that you use to guide the generation of an image, is this text embedding. So all of a sudden you can make, a red bird with a blue beak and it'll do it. Okay, so those are our conditional GANs. Let's now talk about progressive and scalable GANs. So in progressive GAN, ProGAN, the idea here is that these things are unstable, and that's a huge pain. So what if we didn't stick with the same architecture all the way through? After all, we're training these architectures iteratively, aren't we? So what if you started with a discriminator that had one hidden layer, right? And the generator only had one hidden layer, and we just get the best that it can do. We train till it sort of lowers its loss curve. And then, since we're training these things back and forth iteratively anyways, you then add another layer, right, to both of those, and you allow it to get even deeper, and you train it again, and then you add you don't have to just add layers. You can add complexity in other ways, but that's the idea. We're going to progressively make the architecture gnarlier, because if you hit it with a really big architecture and a ton of parameters, the likelihood of it diverging is pretty high. So this was a really clever idea. And this was a way to, in essence, start with like low-res images and add layers to high resolution. It's not exactly what they did, but pretty clever. You're growing the networks themselves to stabilize high-resolution training. So there's a Celeb A HQ. They train off of celebrities, actors, and this is that database that use this. Style GAN, I just mentioned turning me into Studio Ghibli. This is now largely using tools like Style GAN. So that stands for Adaptive Instance Normalization, which is really just a tool for mapping key features and doing that separately from the style inherently with them. They separate out the content for the image from the style. And then what you can do in the GAN is learn the difference between each of those. Obviously, you want to minimize the difference between the content because you want the overall image to be basically the same. But then you want to minimize the difference between a new style and the original style of the image. So by separating those terms out, you're able to achieve photorealistic faces, style mixing, video generation. And then big GAN just scales GANs with really big models and huge amounts of data. So big GAN was trained off of ImageNet, which is a massive amount of data. And basically the point of this one is you can just get really high quality images coming out of it. Okay, category 4 is our regularization and our stabilization. So spectral normalization, we already talked about. Least squares GAN, this one, it replaces the cross entropy loss. So normally if you're classifying something like this is a rock salt versus a spinel, or this is a picture of a dog versus a cat, we use binary cross entropy loss for our loss. This replaces that with a least squares loss, which gives us smoother gradients. So the benefit here is that you get rid of this vanishing gradient problem, improved quality. And then there's energy-based GAN. We're all scientists. We know that the underlying thing that connects all science is that there's energy, right? Things happen because it lowers the energy. So that's exactly what they do. Instead of treating things in terms of arbitrary loss values, they actually try and map it to an energy function. And solutions that lower the energy become your real data, and things that are higher, or not fake materials, are higher energy. Pretty clever way to think about the loss function. This now becomes a margin-based loss, and you get encoder-like discrimination. So better training, basically. Category 5, as I see it, is GANs that do special things with special types of data. So for example, 3D GAN is now a GAN that works with voxels. We're not just working with pictures anymore. It could be higher dimensional space, like 3-dimensional or higher. So this works with grids, point clouds. This was optimized for that by introducing 3D convolutional nets, and this was obviously quickly expanded to n-dimensional convolutional nets. There's video GAN, VGAN, where the thing here that this does that's unique is it introduces sequential data and its ability to work with sequential data. So frames of a video becomes not a problem. And then audio GAN does the same thing, but with audio waveforms and spectrograms. Okay, category 6 is going to be our hybrid GANs with other models, which is pretty cool. So one of my favorites is VGAN, right? VGAN combines a VAE, which I assume this week you've heard about variational autoencoders because they're popular, with a GAN. So a GAN, what does it have to have? It has to have a generator and a discriminator. So a VGAN basically says, well, the generator, what if the generator itself was a variational autoencoder, right? After all, the variational autoencoder can generate something. So they replace the generator with a VAE to create VGAN. It's pretty great. It has the benefit of encoding it down to this really small latent space, which has some benefits. These work pretty well. There's also GAN and diffusion, right? You can combine GAN and diffusion together. In this case, you're integrating the GAN with the diffusion process for higher quality generation. Basically, the GAN accelerates your diffusion sampling, and the diffusion stabilizes the GAN training. There's GAN and reinforcement learning. I'm going to have some examples of most of these later in real papers in a moment. And again, this one, you're using the policy that comes from your reinforcement learning to optimize through reinforcement learning. You're going to come up with policies for the generator and the discriminator that get governed by reinforcement learning, which is going to give you some real benefits, right? And then there's GAN and self-supervised learning, which allows you to do GANs with basically less data, which has some benefits as well. And then there's just some unusual architectures like this one. Like you'll see things like this where the discriminator is taking in real data and generated data simultaneously. Normally, we're trying to have the discriminator turn out which one's real versus which one's fake, so you take them iteratively, but you could send them together. And in this approach, what they're doing is by sending in X represents real data, right? So you have some expectation for real data going into your discriminator. Z represents latent space, which goes through a generator. And by sending these through together, what you're trying to do is force the generator to learn to better match the distribution of real data. So there's some strange, intermediate architectures there. And then the final one would be domain-specific or task-oriented GANs, things that do very specific things, like an adversarial autoencoder, where in this case, you're using the GAN's ability to match distributions to learn the latent distribution of an autoencoder. Or domain adaptation GANs, where same thing, you're trying to align the source and the target domains for cross-domain tasks. In all these cases, you're taking advantage of the generator's really powerful ability to learn distributions, and you're using that for something. Last one I'll say is anomaly detection GAN, where again, if you've learned what the distribution for a real material is that has no defects, all of a sudden, if you introduce something that has a defect, microscopy, it has a flaw or a crack or something, it should flag that as out of domain, and it does a pretty good job of that. Okay, seeing some sleepy faces. So let's pause and take some questions. Yeah. It depends is the answer. I wish I could give you like a number to use, but it totally depends on how challenging of a task you're giving it, the dimensionality of your data, how big of an architecture you're working with. Like all three of those things really change how much data. As usual, the more data, the better. In practice, I wouldn't try any generative model with less than 10,000 data points and expect really good results, which is a bummer, but that's, I think, what it is. Maybe you could get away with some transfer learning, like some of these adaptive GANs, train on something big, try and map the distribution, pray to God that like it's going to be somewhat similar. I don't know. Maybe get away with that and reduce your data set. But generative models in general, right, are all pretty data hungry things because your whole principle is that you have two tasks: learn a distribution and then realistically make variations of that. And that just takes a lot of examples to learn that. especially as you increase the complexity. Other questions I can answer so far about the different types of specific GANs out there? Yeah. For the score, it's unconstrained. You let it be any number. Not even positive, any number. Yeah. Yeah, because let me actually show you with an example. Let's jump over to, I've got a Colab notebook. I was going to say this then, but let's take a look at it now. So I'm going to run this Colab notebook. We'll give it a second. You should have access to this. I think they shared it. So if not, I can send links to this, make it a little bigger. Oh, he's sending it now. What he is. So in the beginning, by the way, here's some examples of some of the stuff we saw. Like here's Cycle GAN, takes a Monet, turns it into a photo, or vice versa, right? So I walked through how to build a GAN here at first. So I'm going to jump past how we build a regular GAN and come down here to the Wasserstein GAN explanation at the very end. Forgive all the scrolling, making your head spin. All right. So let's just go through this. I think you can see that. Let me make it a tiny bit bigger. So I'm going to define a function that calculates the Wasserstein GAN, Wasserstein difference, okay? Now, I've already said before, this is not the true Wasserstein distance. This is a super low fidelity approximation of Wasserstein, but we're going to use it. So we have our D and G, that stands for the discriminator and the generator, which we created up above in the code, which, take my word for it, I made them already. We'll show you later how they look. We right now have a list of real scores and fake scores that are empty. We just have a place to put them. And then in the function itself, we're going to use torch and we're not going to use gradients, right? Because this doesn't require gradients, okay? We're going to go one by one in some batch size, one by one through all the samples in our X real, that's some batch size of real samples. We're going to go one by one through them, and we're going to, let's see, we're going to pass them into the discriminator and collect its score. So the discriminator outputs a number on the number line. It's not squeezed between 0 and 1. It doesn't pass through a sigmoid. It's just a number, okay? We're going to append all those scores together and turn it into a NumPy array. This is just making sure the batch size equals, right? So that's that first section, okay? We've just sent real samples through the discriminator and collected their score of that final node. That's all that's done. We're going to do the exact same thing with our fake scores. So again, we usually call this Z, where we're going to come up with random inputs. We're going to send those through the generator, G of Z, to create fake data. We're then going to take that fake data, xfake, and send it into our discriminator and collect those scores. And we're going to store those into a list. So this next line of code where it says real scores, fake scores, we've just taken however many our batch size is. I think our batch size was like 64 here. So now you've got 64 numbers that represent real data, what they come out of the discriminator, and 64 numbers that represent fake data. So then the last thing we do, this is it, like voila, this is your magical Wasserstein distance. That's so not the real Wasserstein distance, but they're just taking the mean of the real scores minus the mean of the fake scores, right? That's what they're doing. Now I visualized this and I just took those real scores and fake scores and I plotted them into histograms just so you can see. And you can see that here's what those histograms look like. Let me make that a tiny bit smaller, right? You can see that the average of the blue and the average of the pink are not at all the same, right? It would be better if we instead tried to actually fit these to, say, like a normal distribution or something, and actually do a cumulative distribution function and take the error into the curve, but that'd be a lot more math. And this is already happening every epoch, so they didn't want to do a lot more math, so they just took the average, right? And depending, I actually ran this morning, and these two things were almost right on top of each other. So it clearly, there's some variability here. Depends on what the random seed is, right? But you can get it to be a close match or very different. But you're just taking it, you're gonna take the average, you're just gonna subtract it. Okay? Keep going. All right, let's keep going a little bit longer. So I'm gonna, because I'm a material scientist, I'm mostly gonna tell you about material science applications of GANs, right? And there's a whole bunch of them. Organ, talk about, oh, where is it? Here we go. Organ is, this comes from 2017. It's for discovering new molecules. They're combining GAN with reinforcement learning. The reinforcement learning allows you to introduce penalties for things that would be hard to encode into your molecular design, like Synthesizability would be a good one. Like, it's one thing to represent a molecule either as a crystal graph or whatever you want to do, but how do you represent synthesizability? Well, you could actually assign a score in a reinforcement learning architecture using computer-assisted synthetic design protocols or different tools that are out there. And in a reinforcement learning framework, that then allows you to set via policies in the reinforcement learning what the weights of the generator and discriminator should be. A couple of things here. They used an RNN architecture for the GNN. The discriminator had a CNN. They trained this on 5,000 molecules and got away with it using the Zinc database. Admittedly, this was the Zinc database is a smaller subset of all molecules. This was not quite as wide open. So they gave it, in essence, an easier task and got away with less data. That's usually the trade-off. If you don't have as much data, you have to sort of tame your expectations of what you can do with the model. Yeah, and some of their objectives in the reinforcement learning were solubility, synthesizability, and drug likeliness. So here's a pharmaceutical attempt, okay? Here's another one, MolGAN. MolGAN generates molecules using graphs directly. It avoids the typical approach, which is smile string. One of the common ways that we represent molecules is with smile strings. Basically, turn the molecule into text if you're not chemists. But a better way to do that is to represent them as graphs, and that's what this is doing. By doing that, you avoid problems of like a text can come up with nonsense text. I'll show you an example of that later. Graphs tend to have valid outputs. And then they use, again, reinforcement learning to steer towards desired molecules where that could be specific activities or functions or synthesizability. Here they trained on the QM9 dataset, which is a much bigger dataset. That's tens of thousands of molecules. How about this one? Mol cycle GAN. We already mentioned cycle GAN. Cycle GAN was something that cyclically learns how to encode A to B and B back to A. The classic example is zebra to horse, horse back to zebra. So here what they're doing in this mol cycle GAN is they were able to generate molecules based on some input molecule. So imagine that you know what a great drug is for treating cancer, and you're another company that wants to get in the market. This is a way for you to say, here's the molecule that works. Now, generative monomer, give me other molecules that are like that one, not exactly the same, but like it. And then maybe one of those will also work and you could compete in that space. So this is sort of like an IP defeater machine, right? Works pretty well. There's MatGAN IP. This one uses a GAN to learn real versus fake property data to then eventually generate labels that could be close to real. So pretty cool. Like basically, the discriminator's job is to learn real versus fake data. So then once the generator starts generating structures and you have the ability to generate labels that you sort of trust are real versus fake data, okay, generate a bunch of things, see what their labels are, and maybe then that's a real material, even though it's something that's been generated, which is kind of clever. How about this one? Cubic GAN is a pretty simple one, surprisingly. It got published later, but it didn't do as much. It's a GAN that only generates cubic materials. They trained off of DFT data of only, so I think you mentioned like how do you represent all materials? In this case, they didn't here. They only represented cubic materials. And they were able to rediscover some training points that had been held out. Sort of just an okay work, I think. MatGAN uses a GAN to generate compositions. It had a really weird representation, like you have to zoom in to see it. But basically, instead of doing the normal composition-based feature vector, which in our world is pretty typical, they did a one-hot encoding of the chemical formula. But some formulas have more than one element. It might have like 6 or 7 different elements. So they had like one-hot encodings with like 6 columns, like this massive goofy way to represent chemistry. I think it's a goofy way to represent chemistry, but technically you can do it. They trained off of a bunch of data sets, quite a bit actually. And they showed, the blue versus the red data points here. The blue is the generated, let's see, forgive my font is too small. So the green data points of the train, I don't know if you can see any of this. There are green data points here. Red were the leave one out, and then all the blue is the space that they generated. Now, do I believe that all these blue data points are real chemistries that could exist? I do not. I think a bunch of these are probably nonsense chemistries, but it's a way to generate them, and you could always screen afterwards. How about this one? They used a conditional GAN to create high entropy alloy phases. They got encoded the phases got encoded alongside the representation. So they're not only encoding the chemistry of the high entropy alloy, they're encoding which phase is present at the same time. And so the GAN is able to learn both of those simultaneously. You see that they've got your prediction of both your phase and your composition here. We see this all the time in microstructure. They use Wasserstein GANs all the time to generate synthetic microstructures, where again, like going to the lab and capturing these 3D microstructure images of materials is a huge pain. You're doing something like CT scans, or you're ablating layers away using like the tri-beam tools or atomic. Like there's technically you can do it, but generating tens of thousands of data points is not going to happen. So instead what they do is they generate a small number of data experimentally, and then they allow a GAN to generate microstructures that look like your real data and use that for future model building. It is synthetic. This is data augmentation. They're coming up with fake data, but the hope is that they're able to generate fake data that looks like the real thing. Okay. How about this one? So this is where they combined a Wasserstein GAN generator with a variational autoencoder latent space to improve the stability, and then use this for reconstruction of crystal structures. This one, relatively recent. This was pretty interesting. So they combined a GAN with a genetic algorithm. Have we had a lecture this week on genetic algorithms? I don't think I saw that on the program. It kind of gets held out of machine learning, but I think it's pretty cool. Genetic algorithms are pretty awesome. Essentially, in genetic algorithms, you always have 4 components. You have to have like crossover. You have to allow, basically like in nature, right? You have like 2 parents, their genes mix. There's some degree for mutation. Stronger species have to survive, so there's a selection. Like all those 4 core rules, you can encode that into the ability to generate new materials as well. The fitness function says like stability might be a good fitness function. When you come up with some crazy new material and you were to do a DFT relaxation on its structure, if it's a nonsense structure, that's like not a fit material. So it would not compete. It would not be able to pass its genes forward. But if a stable material exists, that would be an example of a decent fitness criteria. So what they did here is they combined a GAN and a genetic algorithm to sort of get the best of both worlds. If you look at it, right, they've got their selected solutions down here in the bottom left. Mutation and crossover comes up with some new genotype. This is a new material. That goes into the generator, right? The generator comes up with a phenotype and predicts properties with some sort of gradient-based approach. So now you've got predictions of properties. This could be mechanical properties or whatever. You figure out which ones are the best, have the properties you care about, like the highest strength and the lowest density. That leads to a next round of your best, most fit parents that then come up with new rounds of children. So it's a clever way of doing a genetic algorithm. Normally, a genetic algorithm does not include this generator step. It just goes straight from mutation to evaluating properties. The generator step is a clever approach here. And why do they do it? Because it reduces the dimensionality. The generator can squeeze this down to some lower dimensional space. So it fixes the problem of high dimensionality that you see with genetic algorithms, which take forever. Because just like in nature, for change to happen over species, it's like thousands of years and many, many cycles of like procreating and making next generations. Genetic algorithms, their biggest downfall as I see it is that they are hugely computationally intensive, because to get meaningful evolution of something better, you're just doing a lot of calculations. And the higher the dimensions, the worse that is. So here they fix that by squeezing it down to it. That's a pretty clever approach, right? I actually like this paper. This is a conditional GAN that steers the generation towards specific spectra and nanostructures. So they're coming up with new molecules. And again, the CGAN part of the conditional generator is based off of spectra. So it's a way of, just like cycle-to-cycle GAN said, this molecule's the one we can't use, so make things like it. Here they did something similar, but they used information about the molecule, the spectra, right? That could be Raman spectra. What did they do here? I don't remember. It was, I don't remember which spectra they used, but it's some sort of characterization about the molecule, and they used that to guide it, which was pretty clever. Optical spectra, ionic conductivity, and photoconversion efficiency. Here's this one, Cardigan. Love that. Compositionally complex alloys, that's just another word for high entropy alloys, just metals where a bunch of elements are pushed into it. What they're doing here is kind of clever. So the generator is taking in your random noise. It's making synthetic compositions only. That composition, we then modify it to come up with a feature vector by doing this empirical parameter calculator. So in comes a chemical formula. We want to turn that into something chemically meaningful. That's what that purple box is doing, the empirical parameter. Meanwhile, we're taking real data. So both of these come up with our real sample data set. Both the fake data and the real data both have this empirical parameter calculator. So now you've got both data sets. And then they have 2 different discriminators. One based off of, this is just composition only, this top one, and the lower one is the phase present. in these alloys, we don't just care about the chemical formula, we care about the phase that it has. And so this was a clever way to train both of those simultaneously. That said, even state-of-the-art generative adversarial networks, which you've spent a long time training and messing with, can still really mess up. Here's an example. This paper was specifically trying to figure out how good they are at things. So what you're seeing here is histograms that show different materials that have been segmented out of images. And if you have real images, that's shown in blue up there. So in some real images of whatever, I don't know if this is ImageNet or where they took it from, you can see what types of things were present, like walls were super duper present, beds and floors, all the way down to the less common things like seats and desk. But in red, what you see is the output of segmentation when you ran a generative model trained on the exact same data. But what do you see is that randomly certain things just don't show up, like chests or canopies. Canopies just do not show up in your GANs. And you wouldn't have known that by looking at the output, because you have to look at the aggregate of a lot of these things and use some sort of statistical collection of these outputs to catch something subtle like that. So what this tells me, my takeaway is like, even if my GAN's looking pretty good, I should be skeptical maybe a little bit of it and wonder if there's a blind spot that I'm not seeing. So I like this paper that they systematically go through and they try and catch what's missing. And again, these are two different benchmarks. One was done on Wasserstein GAN with gradient penalty. This one over here was on style GAN. We know that style GAN is going to do better because the whole point of style GAN is that it preserves features, which are the objects in the image, and it just puts them in a new style. So look at the performance. It basically captures everything. So think about what you're asking your generative model to do and ask yourself if this is going to be important, if there's an unseen bias that you're not, aware of. And then lastly, I think the last thing I'll say before I move on to another example is there's always a trade-off between cost and accuracy. You've heard it all week, I'm sure, in deep learning. And it's a tricky one, right? As you increase parameters in size, it gets better, but computational cost can get pretty wild. I did add this one more this morning. I thought this was another cool paper. So I do a lot on high entropy alloys. And again, the typical task that we're interested in high entropy alloys is we want to classify, when you mix these different random elements together, is it going to give you a single phase, multiple phases, or an amorphous phase, meaning it doesn't crystallize at all? So this paper from 2021 tried to do that. They came up with a data set of 989 data points after they dropped out duplicates. Those were not evenly spread across 4 different classes. Like there's 250 that formed a solid solution, 267 that had a mixture, 307 that had intermetallics, and only 165 that had amorphous phases. But it's not crazy. It's like kind of an okay mix here. They tried to predict which phase it would form in with a bunch of different things like deep neural nets, and you can see their architecture, how they did it. But then they introduced a GAN with the generator and the discriminator with those parameters to balance the data set, which I thought was pretty cool, because this paper on its own I wasn't like wild about, but when you dig into it, they modified their data. They used a conditional generative adversarial network to do data augmentation. So again, on this one, you can see, so in this bottom left figure over here, the SS are the blue triangles, and then the plus marks represent generated solid solution. So they were able to generate more data that sort of matched the distribution of data they had from to then balance their data set when they built a model to classify these things. I think that's a pretty good idea. And they showed that it did better, right? Here's comparing the straight up regular model had 84% accuracy. I do not think that they had 4 sig figs of confidence in those numbers. I'm sure there's error bars that they're not reporting. But they show that when you augment it with whatever augment 150 is, that they improve their accuracy by about 10% or so, which I think is probably realistic. I probably believe those numbers. I'd believe it more if they actually ran it with multiple data splits and showed the variation. But I'll bet that you get about 10% improvement by doing this. And then ultimately, they actually made some materials and showed that the output, the predicted phase which they had, matched reality. When it predicted that it would be a solid solution, it was. And when it predicted that it was going to be a mixture of solid solution and an intermetallic phase, it was. Now, is that everything that they reported? I don't know, because I don't trust anybody in the literature. But as much as they said, that's pretty slick. Okay, it's 10:08. We go till 10:30. Maybe I've got more to say about generating crystal structures, but let's just briefly walk through the code. I think that might be more valuable on how these things get made, because they seem kind of scary, but they're really not too bad to synthesize. So let's come up to our code and walk through this. So I'm going to do this in PyTorch. I do PyTorch for almost everything. Some people are other, Jackson, whatever else, and that's fine. The big thing about PyTorch that I like about it, and why I think it's fantastic, is that it preserves the operations that happen to your tensor, so that calculating the gradient is as simple as doing this backward command, which is huge. That makes the math of backpropagation very easy. So we bring in a bunch of PyTorch libraries. Let's see, it's come right down here. So I can skip the example of PyTorch and its awesome ability to do automatic gradient. Okay, here we go. We're going to define our discriminator. So we're going to create a class called discriminator. This is going to inherit from PyTorch, from the neural net module. So we initialize this thing. The input dimensions in this case is 784, because the data that I'll be working with is part of the MNIST dataset. If you're not familiar with that, there's a bunch of them. There's like the handwritten numbers. In this case, we're doing the fashion MNIST dataset, which is a little less common one. It's grayscale images that are 28 by 28 pixels of clothing, right? That's what we're going to be training on. So 784 is just 28 times 28. So that's the input dimension. We're going to take all this overall image, and we're going to break it up into lines, put it all into one big long vector. That is the input. So our discriminator input dimension has to be that size. If you look at the model itself, it's not that gnarly. Like, the model consists of only a fully connected network, that's FC1, where we do a neural network linear, where the input dimensions are 784. We're going to set that down to 128 nodes. We then have a nonlinearity. This is the activation function. In this case, we're doing a leaky ReLU. A ReLU, again, is 0 if a negative number comes in, and it's proportional if it's a positive number. A leaky ReLU is not 0. It's just like -1/5 times that value if it's a negative number. So it basically penalizes negative numbers and allows positive ones to go forward unchanged. And then there's a second fully connected network that goes from 128 nodes down to 1. So super simple neural network is our discriminator here. There's not much to it. And then we have to describe some text that describes what happens when you pass data forward through the neural network. We're just connecting those tools that we built before. And then we add one last thing at the end. When we're finally done, we pass it through a sigmoid. Again, our friends in computer science love sigmoids because it squeezes things between 0 and 1 with very little ambiguity. So from a classifier perspective, we like that. We want it to be either a 0 or a 1 with not a lot of ambiguity in between. So that's our discriminator. Then comes our generator, also going to be really simple. The input now is going to be different because we don't have to deal with real images when we come in. In fact, it's more common in the literature. You see that they usually do a dimension size of 100 if you're coming from your latent space. But we're going to have to upscale that to 784. Just like the discriminator took in 784, which is a 28 by 28, the generator has to generate something that's 28 by 28. So at the output of it, it started out with 100. It goes to 128 in the middle. But by the end, it's going to go from 128 up to 784. So it's going to try and create our fake image like that. And just like before, we have our fully connected forward pass through. We end it with a tanh, right? A hyperbolic tangent function instead of a sigmoid, because we typically want the pixel values between -1 and 1. That's sort of standard in working with images anyways. You don't have to do that. That's just what they do because it's common with images. So great, we've defined those functions. Let's initialize them. We're going to create 2 Python objects, D and G, which represent our discriminator and our generator. It's got them. It tells us what they are. 2 really simple neural networks is all they are, okay? So let's test them. We could take, right, we're going to use PyTorch to generate random numbers taken from a normal distribution. We're going to have 5 samples with 1 layer, and they are 28 by 28. And you could pass them through the discriminator by sending those samples into the discriminator. And here they are. So the output, the discriminator thinks of these random numbers, that here's the output. What do you see is that it doesn't know what they are. It puts them kind of right in the middle. That's good. Because again, we just took these numbers randomly from a normal distribution. We haven't biased the model yet because we haven't done any training. So it shouldn't tell us that they are 1 real or 0 fake because it hasn't learned how to do anything with it. It's just taken random numbers based on its initialization. So the fact that they're landing right in the middle around 0.5 is sort of a sanity check. Okay. Okay. By the way, your discriminator, because it's PyTorch object, we can easily pull the parameters, like what are the weights? What are the biases in the first neural network? Or what are the weights and the biases in the second? We can separate those out and we could visualize those if we wanted to. Same thing with the generator. Okay, how about this one? So let's take a small batch of 2 samples, random noise. So this is going to be Z. Anytime we're seeing Z, that represents our latent space, so fake data. We're going to take those randomly, 100-dimensional objects, 2 of them, pass them through our generator, and then we can look at them. So this now represents, this is like an image, right? This is the fake image, right? Now, if you plotted that as an image, it would actually be a grayscale image, but that's the values that are coming out of our generator. Okay, and here they are, right? Without having trained anything, these don't look like clothing. Our goal is that during the training process, we want these grayscale images to eventually start to look like clothing, okay? Right now they don't. Okay, so let's grab real data to train from. PyTorch has fashion MNIST available, which is one of the nice reasons why we like, another reason to use Torch Vision. It's got these data sets available. So we're gonna grab it. We do a simple normalization. This normalize 0505, all that does, it forces the pixels to be between -1 and 1, which is exactly what we did with our generator with this hyperbolic tangent up here. This forces them also to be -1 to 1. So that's just a normalization step. So we've grabbed some data. We've also defined a couple things in our data loader. You guys know that when you work with neural networks, it's not realistic to pass all of your data through when you do your backpropagation. So we send it through chunk at a time. The data loader allows us to do that chunk at a time. We're defining our batch size as 64 and we're shuffling the data. Okay, so now we can look at some specific index, right? One of our data set, the data set at index number 149, whatever that is, and we can plot it and you can see that it looks like a shirt, right? And this is only a 28 by 28 pixel grayscale image, so it's not great, but it looks like a shirt. Great. So we've got some real data. And we could actually take that real material, right? And we could send it through our discriminator and plot the score. And again, it doesn't know if it's a real material yet. It says that the score is 0.48, so almost half. It doesn't know if that's real or fake because we haven't trained it yet. Let's see, that's just more batching stuff. So here it's showing us 64 examples of real materials, right? 8 by 8. So here's the type, that's the type of stuff that we're going to be training on, real pictures of clothing. We're going to skip the interlude where it talks about the amazingness that is PyTorch for doing backpropagation for the sake of time and come back to Minimax. So earlier today, I said that the goal is with that function, the generator wants to minimize the output of that function and the discriminator wants to maximize it. So we need to calculate this thing. So let's show you how that works. Down here, we've got the same discriminator and generator that we generated before. We do have to tell it what optimizer to use and what conditions to use. So the only thing that we're going to do, that we're going to tell it, is just give it a learning rate. A learning rate, as you know from backpropagation, just essentially tells you how much to nudge the weights each time. Larger learning rates learn faster at the possibility of divergence. And again, that are prone to diverging, that's a bigger issue. So smaller learning rates are good. Or use a progressive GAN that changes those over time, sequentially updates them. As you're getting more confident, you can risk larger changes, but start small. Okay, so we've got our generator and our discriminator. We have to define a criterion, a loss criterion. So we're going to use binary cross entropy, but there's others that you could use. And right here. So I told you that these things these things get scored sequentially. So let's see that in action. The first step is we're going to optimize the discriminator, not the generator discriminator. So we have to start with real data then, if we're dealing with the discriminator. So we're going to load some from our data loader to get 64 examples of 28 by 28 images. We're going to take those and we're going to have our real data. We're going to assign them labels of 1, right? So we're going to create a torch tensor filled with 1s, right? Those are the labels. We're going to create a torch tensor filled with 0s that we'll use for our fake data in a moment, okay? We're going to reset the gradient because this might not have been the first pass through the epoch, like you're training this over and over. You want to reset the gradient each time. The first thing, once we've done that, is we send our real data through the discriminator to get the output. And then, once you've got that, we're going to use our binary cross entropy, that's our loss criterion, with the output of the discriminator and what the labels were actually. it's going to then calculate the loss of the discriminator. So the loss D real is the discriminator's loss based off of real data. But then we do the exact same thing, but this time we're going to do it with fake data. So we're going to generate our fake data. We're going to send it through the generator. We're going to detach this because we don't need the gradient of our generator because we're only updating the values of our discriminator right now. So we don't need that backprop tool. We're going to send the generated samples through the discriminator. So it's taking the fake data and running it through the discriminator. And then just like before, we're going to use that binary cross entropy and compare the labels that came out of the discriminator on the fake data, take them to the latent space with the actual labels. Whew, it's a lot of work. And at the end, you end up with this. The overall loss is just you add the loss of the real data with the fake data. Now, when I saw this, I was like, hold on a minute. That doesn't look like this equation. There's no logs. It should be actually 1 minus that one. Why did they just add those together? The reason why they did what they did is basically that we're not seeing what's going behind the scenes here. Binary cross entropy does that for us. The mathematical operations that you're not seeing happen in binary cross entropy, which allows us to simply add those two terms. So it's actually, they're not cheating, they're actually doing it right. Once you've done that, once you've got your loss, that's the magic right here. This backward command is why we use PyTorch. You can just take that operation on these matrices, as big as they are, loss.backward computes the gradient for all of them. And then using that, the optimizer, all you have to do is dot step, and that will then use the gradient to update the discriminator's weights. Pretty elegant, I think. That's pretty cool. And then step 2 then is we're going to do a similar thing with the generator. But remember, with the generator, we don't have to worry about real data because the derivative only ever uses the synthetic data for the generator. So we start out with fake data. We send to the discriminator our fake data that has gone through the generator. So now we get this D of G of Z, right? And we calculate with our criterion, our binary cross entropy, what the loss is, and we use that to backpropagate so we can update the weights of our generator. Okay, everybody with me so far? It's not too bad. Or like 100 lines of code in, it's not too bad. So then once you've built those, you can actually run this thing. So this thing ran in 1 minute. I only let it do 3 epochs. Where did I define that? So here I'm defining the discriminator again. I'm defining the generator again. I'm telling it to put it on GPU if it's available, CPU if not. I send those to whatever device is available. I pick the optimizers. I picked really low learning rates because I don't want it to diverge. Tell it which loss function to use. Tell it which data set to use. Grab your data loader. Collect data as you go, basically. And then I added a small function to visualize things. We want to plot these at the end. And here we go. We are going to train 3 epochs. 4 epoch in range 3 means we're only going to train this 3 times. Obviously, in the real world, you're going to train it tens of thousands of times, right? Monitoring your loss curves, and when you stopped improving, then you stop. Here, just for the sake of simplicity, we're only running it 3 times, but it's just following our steps. It's doing exactly what I showed you separately, but it's doing them now sequentially in order. And here's the result. So the output, again, I just ran this on a CPU, but E0 stands for epoch 0. And you see it does it. There's 938 samples that we were doing, 64 at a time. And you can see the score of the discriminator and the score of D of G of Z at each interval. And what we're trying to see is iterative improvement of both. But you see it's jumping around all over, right? It starts out at 0.4. That score climbs clear to 0.9. Sorry, the D you want to go up. D of G of Z is going down. So it's actually looking like it's working. We go to epoch 1. It's doing kind of something similar, epoch 2. And when we stop, then we plot the output of our some of our generated samples. And, you know, they don't really look like clothes, but that's because we only trained for 3 epochs, right? Had you let this train over and over and over, eventually there's enough data here, you could probably get things that look like real clothing. So not too bad. I don't think it's too bad. In practice, the more complex your challenge, the more higher dimensional your data, this can get worse, but that's at least what we've got so far. Any questions on this? Yeah. Yeah, that's just a 2-dimensional, very simple image. So again, pixels came in between -1 and +1, and there's only 28 by 28. So this is a very easy representation. Let me just, in the 8 minutes we got left, let me just give you a flavor of what a harder real scenario looks like. So generative models for crystal structures have become very popular. we've published in this area. Here's one that we're proud of. The big problem what was missing up until just a couple of years ago is that we didn't have a representation, a way to represent the molecule or the material crystal structure that allowed for periodicity. It's one thing to do it with a molecule, right? That top left is some molecule. And they were able to, with reinforcement learning, to treat this kind of like Legos, and they could put building blocks on and have generator models that would generate a molecule. But oftentimes the properties we care about don't just depend on the molecule, but how those molecules stack together, the crystallinity of the periodicity, like the crystal that forms. There was no way to represent that. Without a way to represent that, we had serious problems. So ourselves and a group at MIT were in the same year able to come up with a clever way to fix this. We both used crystallographic information. So I'm going to jump ahead and show what it looks like. In the material science world, the way that we represent crystals is actually pretty straightforward. There's a text file you can open up, and it basically looks like this. What you're seeing there is the ABC, that's the dimension size in the like the XYZ directions, like how big is this shape? And then what type of shape are we talking about? Like, is it a cube or is it tilted? You have to have the angles between the axes. That's alpha, beta, gamma. And then you have to have this space group number. That's where the magic happens, right? That defines all of the symmetry so that you can start with actually a pretty small number of atoms. Like this is telling you it has selenium, indium, and copper located in the following X, Y, and Z positions with some occupancy. So that's not very much information, but you can go from that 3 atoms to this structure that it will continue infinitely by adding the space group. It will add through symmetry where all the other atoms are, like will it be a translation or a rotation or whatever else. There's all these different things. So in other words, that's not a lot of information. So in the early days when we did this, we thought, well, we can get that information. That's not so bad. I could come up with an input representation. And we tried this. This was way back during COVID. We weren't very good at it yet. We basically said, all you've got to have is room for ABC, alpha, beta, gamma, the space group number, and then as many columns as you want to represent unique atoms that you need in the basis of the structure. That's where it gets a little tricky. This guy up here asked, like, what about simple and complex structures? That's exactly this problem. Some structures like carbon, diamond, has 1 atomic position. You tell it where 1 atom, in fact, you put it at 0, 0, 0, and it does all the rest. But others can have up to 200 different unique atoms in the basis, let alone how many are in the unit cell. So the way that we got around that is we only went up to 52 different atoms in the basis because that captured like 90% of the structures that we had available to us. And we just padded them with -1s. You could pad it with zeros. We found -1s worked a little bit better. So technically, we could have gotten away with just a single vector representation. What you see here is a matrix, and we just found that by averaging it over multiple times made it more stable. And stability is the name of the game with GANS. That said, we did all this work. I'm going to skip some of the drama we ran into. And the very first one that actually converged, when the GAN converged, Anubhav might have been there. I showed this in 2021 or something in the MRS fall meeting, and it was super bad. Like, this was the first one that converged. That's nothing like a real structure. And neither were the ones that followed. Even though my student was adding batch normalization, he was adding LST only. He was modifying the architecture, and none of it was working. The big difference came, like sort of on this timeline, I'd say that was like sort of the early stuff. And the big problem was that we were using a vanilla GAN architecture, which again, you're praying that this sigmoid function at the very end, that final node value, when you send it through this mathematical sigmoid, that it's going to be able to get it right, real versus fake. And today I've showed you that a much better way to do that is with the Wasserstein distance. The benefit here is many. It's just a better measurement of real versus fake. And one of the problems here is that if something's really bad, the slope of that line is your gradient. The gradient is what you use to update the parameters in your model. So this is a vanishing gradient, right? The more and more that you know that it's fake or you know that it's real, the flatter that curve is, you get bad information back. So you don't get useful information to improve your model. An Earth mover distance fixes that. And so it made it a little better. Now we're in 2022. I showed this and it was like moderately better. I think this was actually 2021. It was 2022 that we fixed the symmetry problem. So again, when you have the basis elements and you apply the symmetry, it gives you everything else. But this is where atoms were getting put on top of each other in crazy ways. So the only way to fix that is to change our representation. In this case, we added a direction graph. We gave the algorithm, the network, an opportunity to learn what are reasonable distances between atoms by giving it a direction graph. I'm going to skip some of this for the sake of time. There was a lot of drama, but I'll just show you this. Here's the vanilla GAN output, right? if you take a very simple unmodified GAN, what do you see? You see atoms are on top of each other. The only elements it's using are like rare earths and transition metals. Everything else is not getting used. And it's not using many different types of crystal structures that should be available. The Wasserstein GAN was better. The unit cells are much more realistic in terms of size. It's using all of the periodic table, but it's using stupid stuff like crazy combinations that shouldn't make any sense. And things are still not that great. And when we, in this case, actually switched to a diffusion model, here I'm telling you about the greatness of GANs, but we switched to a diffusion at the end. Although we've since gone back to GANs and they're pretty good. It just smashed it, like way, 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 way better. Here's one way to give you a feel for how good they are. What you're seeing here is 3 plots of the elements available from the periodic table on the x-axis, and it's a histogram of which ones and how many there are. So the generated versus the real distributions are the pink and the gray. So the pink, like a salmon color, that's the real data. You can see in that top left one, there's like a spike at element number 8. That's oxygen, right? It's really, really common. And then it dips to 0 at the noble gases, right? So that's it turns out most of the materials we know are oxides because Earth has a lot of oxygen. And it's fairly easy to form and break bond. But the generator was making a bunch of transition metal actinides, right? The Wasserstein GAN was using the whole distribution, and diffusion models were actually mapping the distribution pretty accurately. We saw the same thing with space groups. Technically, there's 230 different symmetry groups, and mode collapse, serious mode collapse happening with the vanilla GAN. Here, the Wasserstein GAN's using everything, but it's not learning that some of them are more common than others. And in this case, the diffusion model we used there was actually learning it pretty effectively. So it got us to sort of here. We've done a lot of work since then. This was back in 2022. I'd say that now we have the crystal structure equivalent of being here. And we ironically have switched to language models to do that, but that's a talk for another day. So what's my takeaway? I think GANs are pretty awesome. I think that they're like genuinely one of the very cool, clever things that scientists have built to learn how to learn distributions and do something useful with them. And so with that, I'll take some questions. I think we're ish out of time.
Maybe we'll take 2 questions, but then, I mean, I guess around it, right?
Yeah, thanks for the talk. You mentioned at the end that you switched to diffusion models, hence you've come back to GANs. So I guess, independent of your area of application, what is the one thing that you would still say is
If you want, which we did, we wanted the structure not to learn the distribution exactly and reproduce it. I think GANs can do a good job of that. Instead, you want the ability to do conditional generation, and you want variability that you can easily control. Diffusion is pretty great, right? Because you can, inherent to the diffusion process is this denoising step. You can sort of guide the creation of, in our case, a crystal structure that has just the properties you want during that diffusion process. That's pretty slick. But if you just wanted to learn a distribution and create members from that distribution, I think GANs are still more powerful if you can train them stably, which is going to be hard to do with these representations. I haven't seen people use crystal graph GANs. I think that they would work better. I think that the mole GAN stuff, that's all, most of that is using graphs. And there's a reason why those work really well. We just haven't been using graph representations in my group. That's just what we've not been doing, though. It's a simpler representation. It's much lower dimensional than what we're doing. It would probably work better with GANs than what we've done. Yeah.
so it's about the kind of work for student problems. So I'm wondering what about particular like behavioral problems? Do you think that
I don't even know where to begin on that question, honestly. I don't think I understand the difference well enough to give you a good answer. Could you elaborate a little bit?
let's say, person inside the private car, bus, or something. It's not necessarily like, it's a little bit like the theoretical problem is not like a situation where it's going to be
But they're probabilities, right? You could frame it as a probability.
can be like that if it's fuzzy. Like you can even like even if you frame it in the temperature, you can say something like hot, but it's kind of like a specific temperature.
I hear what you're saying, but I'm really struggling to think of what,
Yeah,
I don't think I have a good answer for you.
Maybe we can take it offline.
Yeah.
Okay. Okay,
Okay.
great. So thank you again. And I just wanted to share a couple of announcements.